All right, get ready, because today we're diving deep into the world of polymers. But we're not talking about your grandma's nylon stockings here.
No, definitely not.
We're looking at a brand new way to make polymers, something called C1 polymerization.
Yeah, it's pretty cutting edge.
It is. And to guide us through this research, we've got our expert on the line.
Hey, glad to be here. C1 polymerization is really exciting stuff. We're not just stringing together the same old molecules.
Right.
It's like we found a whole new set of Legos, you know? Different shapes, different connectors. We can build polymers with properties that, well, we could only dream of before.
Okay, I love the Lego analogy. So for our listeners who maybe aren't chemists, can we back up a sec?
Sure.
We know polymers are long chains of molecules, like those Lego bricks all snapped together.
Exactly.
And we've always used, traditionally, something called vinyl polymerization to make them.
Mm-hmm.
So what's different about this C1 approach? What makes it special?
The big difference is this. C1 polymerization uses single carbon units as the building blocks. Instead of the 2 carbon units you find in that vinyl polymerization, it's a tiny change, at the molecular level.
Right.
But, it has huge implications.
So instead of our familiar 2-pronged Legos, now we're working with single-pronged ones.
You got it.
What does that mean for the final polymer? How does it affect the structure?
Think about it this way. The way those Legos connect, it affects how strong your creation is, right? How flexible it is. Well, using those single carbon units, it's similar. It can lead to polymers with, enhanced properties, enhanced functionalities, too.
Okay, now things are getting really interesting. The article mentions that C1 polymerization can create polymers with really high molecular weight.
Yes.
And you can control the tacticity.
Tacticity, yeah.
It sounds very technical. Can you break down what that means and why it matters?
Sure. High molecular weight basically means longer chains. And usually longer chains mean stronger materials. It's like weaving a rope. The more strands you use, the tougher it gets, right?
Yeah.
Tacticity, that's a bit different. It's about the arrangement of those side groups along the polymer chain. It's like organizing the Lego bricks in a specific pattern.
You
see? And by controlling the tacticity, we can fine-tune the polymer's properties, like how flexible it is or its melting point.
So it's not just about the length of the chain, it's also about how those building blocks are arranged.
Exactly.
Wow. That level of control sounds amazing. Powerful.
It is. And there's something else. Another remarkable thing about C1 polymerization. We can add functional groups very precisely during the process. Think of it as attaching special tools or attachments to each Lego brick.
Okay.
This gives us, unprecedented control over the polymer's final properties.
This all sounds amazing, but I have to ask, are there any downsides?
Yeah.
Challenges, limitations to this C1 approach?
Well, it's still early stage research. So yeah, there are definitely challenges we're still working on.
I see.
But the potential benefits, they're so compelling. Researchers are very eager to keep exploring all the possibilities.
I bet. And speaking of benefits, the article does highlight some really exciting ones. For instance, they found that C1 polymers, they can have higher melting points.
Yes.
Compared to similar vinyl polymers.
Exactly. And that means they can handle higher temperatures before breaking down, which opens up all sorts of applications where durability is critical.
Huge. And there's another detail about degradability. That some C1 polymers can actually degrade under mildly basic conditions.
Right.
Now, I have to ask, degradable. Isn't that kind of a bad thing for a material?
That's a great question.
How do we make sure these polymers are durable enough to actually be used?
Well, degradable doesn't have to be bad. In fact, if we can control it, that degradability can be incredibly valuable, especially when you think about the environmental impact.
Okay, I see what you mean.
Imagine a plastic, right? But it breaks down harmlessly after we're done using it. That's the kind of future this research is hinting at.
Okay. I'm starting to see the appeal. So are we just theorizing about all of this, or are they actually making these C1 polymers in the lab?
Oh, they are definitely making them. The second part of the article, it gets into the specifics of how they do it. They use these compounds called diazocarbonyl compounds.
Okay.
Think of them like specialized molecular hooks that allow us to link these single carbon units in a very precise way and create those unique polymers, which have, you guessed it, some very cool properties.
Let me guess more cool properties. Hit me with them.
One that stands out is degradability under mildly acidic conditions. We were just talking about degradability in basic conditions, right?
Right.
Well, this adds even more possibilities. It means we can fine-tune how the polymer breaks down depending on where it's used. The environment, I mean.
Wow, that's incredibly precise. Amazing. What else?
Okay, get this. They even made C1 polymers that have electrochromic properties.
What now?
Electrochromic. It means we can change the polymer's color just by applying a voltage.
Color-changing polymers.
Wait, seriously, that's mind-blowing. I've never even heard of that. How does that even work?
It's a pretty cool phenomenon, actually. You see, these polymers, they've got these special molecules inside them. And when you hit them with electricity, well, their structure changes.
Okay.
And that change in structure, it changes how they interact with light, how they absorb it, reflect it. So their color shifts.
Wow. So
Yeah.
we're not talking about some dye or pigment here. It's the actual structure of the polymer itself that's changing.
Exactly.
Oh.
It's like, I don't know, flipping a switch
Yeah.
at the molecular level, and boom, a hidden color appears.
Okay, my mind is officially blown. And the applications for this, I mean, I can't even imagine.
I know, right? It's really exciting. We're just starting to explore what's possible. The article mentions things like, color-changing displays, but it goes even further. Think about it. What about windows? Windows that tint themselves automatically based on how much sunlight there is.
Oh, wow. Or clothing that changes color? Just like that, with a switch. The possibilities are pretty much endless.
This is where things get really fun, right?
Yeah.
Because it's so new. It's like we get to imagine the future of materials right alongside these scientists. And I have to say, I'm pretty excited to see what they come up with.
Me too. And you know what excites Ehime the most? It's not just about making new polymers. It's about changing the way we think about materials at the most basic level.
I see what you mean.
Traditionally, we've always been limited by the building blocks, right? What we have to work with. But C1 polymerization, it changes all that, throws those limitations out the window.
It's like all of a sudden we've got a whole new toolbox full of tools we didn't even know existed.
Precisely. And with this new toolbox, well, we can start to create materials that are designed for very specific purposes, polymers that are stronger, lighter, more durable even. And hey, maybe even polymers that can respond to their environment.
This sounds like a game changer for so many industries. Where do you see this having the biggest impact?
That's the million-dollar question, isn't it? And it's one researchers are trying to figure out right now. The article mentions a few areas, but really it's up to our imaginations at this point.
Okay, well then, let's imagine. What about medicine? Could these new polymers be used for, like, implants? Or maybe even drug delivery systems?
Absolutely. That ability to control how the polymer degrades, that makes it perfect for those applications where you want the material to, well, eventually break down safely inside the body.
Right.
Imagine a stent, right? But it's biodegradable, so it dissolves after it's done its job. No need for another surgery.
Wow, that would be incredible. And what about electronics? We talked about displays, but are there other ways we could use them in that field?
Oh, definitely. Because some C1 polymers can conduct electricity, that opens up possibilities for, I don't know, flexible electronics, printable circuits, even wearable sensors that could track your health in real time.
Ooh, I can already see the headlines. Self-healing phone screens made from C1 polymers.
Huh. I wouldn't be surprised. And hey, let's not forget about sustainability. If we can make biodegradable polymers from renewable sources, well, that could be huge for reducing plastic waste.
So we're talking about, like, a solution to the plastic crisis.
Yeah.
And game-changing medical advancements, futuristic electronics, and all thanks to a new way to make polymers.
It almost sounds too good to be true, doesn't it? But that's the thing about science. It often leads to these breakthroughs, these unexpected discoveries that change everything.
I think the thing that excites me the most about this research is, well, the sense of possibility. It unlocks all these possibilities. We're not just talking about small improvements. It's a whole new way of thinking about materials.
It is. And that new way of thinking, that's going to drive innovation for years to come. It's going to be amazing to see what people come up with as they explore the full potential of C1 polymerization.
It's like we're standing at the edge of a new frontier, and we have no idea what we're going to find. It's kind of exciting and scary all at the same time, isn't it?
It is. It reminds us that science is always changing. And there's always something new to learn, something new to discover.
Well, I'm definitely excited to see where this journey takes us. Now, I know we've given our listeners a lot to think about today. Is there anything else you want to highlight before we wrap up?
I think the big takeaway for everyone is that C1 polymerization, it's opened up a whole new world for material science. Like, we found this treasure chest full of amazing tools.
Yeah.
And now we have to figure out what we can build.
Exactly. It is groundbreaking. It really is. It'll be fascinating to see how it changes things.
Speaking of changing things, I want to leave everyone with a thought experiment, okay? Imagine you're the inventor. You've got this incredible C1 polymerization technology, and you can make a polymer with any properties, whatever you want. What would you create, and what problem would it solve?
That's a great question to ask. It makes you think outside the box, Envision solutions that today seem impossible. Exactly. So, to everyone listening, if you could design a C1 polymer, what would it be? Would it be a self-healing material? Something that could repair, I don't know, like damaged bridges or buildings?
Or maybe a super strong fabric, but it's lightweight? Something that could revolutionize space travel, maybe?
Ooh, yeah.
What about a polymer that's biocompatible, so it could actually regenerate damaged tissue?
Wow.
Or a smart material that could adapt to, I don't know, like changing weather conditions. The possibilities are really limitless.
This is why I love doing these deep dives. It reminds me of how much is still out there. How much we don't know. The future is full of incredible possibilities.
Absolutely. And if anyone's curiosity is piqued, well, you should check out the full article. It's called, the title is a bit of a mouthful. Development of Polymer Syntheses Using Diazocarbonyl Compounds as Monomers. It's in the Polymer Journal.
Oh.
I'll make sure to put the DOI in the show notes so it's easy to find online.
Perfect. And for anyone who wants to learn more but maybe isn't ready to dive into all the technical stuff, a quick search online will turn up a bunch of articles and videos. They explain the basics in a way that's easier to understand.
Right. And don't be afraid to think big. That's what's so great about this field. We're just getting started, really. Who knows? Maybe someone listening will make the next big breakthrough.
That's a great point. So to everyone listening, thank you for joining us on this deep dive into the world of C1 polymerization. We hope you learned some cool new stuff and that you're feeling inspired to, think big about what science and technology can do. Until next time, keep exploring, keep asking questions, and stay curious.